The tail fin ripped away mid-air. American Airlines Flight 587 on November 12, 2001 became a tragedy. This Airbus A300 B4605R aircraft N14053 carried 251 passengers, 9 flight attendants, and 2 pilots from John F. Kennedy International Airport. Destination: Santo Domingo, Dominican Republic. It took off from runway 31L at 9:16 and 23 seconds. Just 1 minute and 52 seconds into its flight, the aircraft encountered severe wake turbulence from a Japan Airlines Boeing 747-400 departing 4 minutes prior. The first officer made several aggressive rudder pedal inputs, pushing with forces up to 200 pounds. There were 5 rapid full left and full right rudder deflections over 20 seconds. The vertical stabilizer, made of composite materials, carbon fiber reinforced plastic, was not designed for such rapid extreme directional changes at experienced airspeeds. At an altitude of approximately 2,500 feet and an airspeed near 200 knots, the structural limits were exceeded. The vertical stabilizer separated from the fuselage at 9:17 and 11 seconds in the morning. This catastrophic failure caused the aircraft to lose control. The plane tumbled downwards, crashing into a residential neighborhood in Bell Harbor, Queens, New York. All 260 occupants on board were killed instantly, and 5 additional people on the ground also died, bringing total fatalities to 265. The impact created immense destruction, destroying houses. The National Transportation Safety Board, NTSB, conducted an extensive investigation lasting over a year. They found the first officer's excessive and unnecessary rudder pedal inputs were the primary cause, creating loads beyond the ultimate design limits of the vertical stabilizer. The NTSB also examined the design and certification of composite materials in the tail assembly. The investigation highlighted the need for improved pilot training to address wake turbulence reactions, especially regarding aggressive rudder use. Modern large aircraft are often better managed with ailerons. The incident was a critical lesson about aircraft control systems, pilot input, and structural integrity. The aircraft's flight data recorder and cockpit voice recorder provided crucial evidence showing the precise sequence of events and forces applied. This accident was the second deadliest aviation accident in United States history and remains the deadliest involving an Airbus A300 globally. The disaster prompted re-evaluation of pilot training for upset recovery and led to changes in aircraft design principles regarding stress tolerance of composite control surfaces. Airframe manufacturers reviewed design philosophies. The 265 lives lost ensured lessons would not be forgotten. Every detail of the 2,500 feet descent was analyzed. Investigators spent months piecing together the story from hundreds of thousands of wreckage pieces. The final report, released October 26, 2004, contained over 200 pages of detailed findings and recommendations. The incident served as a stark reminder of flight forces and the critical importance of understanding aircraft design and operational limits. The tragedy underscored the need for continuous improvement in aviation safety protocols and pilot training programs to prevent future disasters. A plane's tail ripped clean away mid-flight. American Airlines Flight 587 experienced this horrific structural failure on November 12, 2001. An Airbus A300 B4605R registered N14053. It carried 251 passengers, 9 flight attendants, and 2 pilots, a total of 260 souls on board. Departing from John F. Kennedy International Airport's runway 31L at 9:16 and 23 seconds, heading for Santo Domingo, Dominican Republic, a Japan Airlines Boeing 747-400 had departed 4 minutes prior. Just 1 minute and 52 seconds into its ascent, the aircraft encountered severe wake turbulence. The first officer initiated several aggressive rudder pedal inputs, pushing with forces up to 200 pounds. There were 5 rapid full left and full right rudder deflections occurring over 20 seconds. This composite material vertical stabilizer made of carbon fiber reinforced plastic was simply not designed for such rapid extreme directional changes at the airspeeds it experienced. At an altitude of approximately 2,500 feet and an airspeed near 200 knots, the structural limits were critically exceeded. The vertical stabilizer violently separated from the fuselage at 9:17 and 11 seconds in the morning. This catastrophic failure led to the aircraft losing all control, tumbling downwards and crashing into a residential neighborhood in Bell Harbor, Queens, New York. All 260 occupants on board perished instantly, and 5 additional people on the ground also died, bringing the tragic total fatalities to 265. The impact caused immense destruction, razing houses to rubble. The National Transportation Safety Board, NTSB, conducted an extensive investigation lasting over a year. Their findings pointed to the first officer's excessive and unnecessary rudder pedal inputs as the primary cause, creating loads far beyond the ultimate design limits of the vertical stabilizer. The NTSB also closely examined the design and certification of composite materials within the tail assembly. This investigation highlighted a critical need for improved pilot training, specifically addressing wake turbulence reactions, especially regarding aggressive rudder use. Modern large aircraft are often better managed with ailerons. The aircraft's flight data recorder and cockpit voice recorder provided crucial evidence detailing the precise sequence of events and forces applied. This accident stands as the second deadliest aviation accident in United States history, and it remains the deadliest involving an Airbus A300 globally. The disaster prompted a significant reevaluation of pilot training for upset recovery. It also led to fundamental changes in aircraft design principles concerning the stress tolerance of composite control surfaces. Airframe manufacturers across the globe thoroughly reviewed their design philosophies. The 265 lives lost ensured that these lessons would not be forgotten. Every detail of the 2,500 feet descent was meticulously analyzed. Investigators spent months patiently piecing together the story from hundreds of thousands of wreckage pieces. The final report, released on October 26, 2004, comprised over 200 pages of detailed findings and recommendations. The incident served as a stark reminder of flight forces and the critical importance of understanding aircraft design and operational limits for utmost safety. A plane's tail snapped off like a twig. American Airlines Flight 587 experienced catastrophic failure on November 12, 2001. The extensive NTSB investigation meticulously uncovered the immense forces at play, specifically focusing on the vertical stabilizer's rupture. This critical component, made of carbon fiber reinforced plastic, a sophisticated composite material, bore the brunt of forces it was simply not designed to withstand. Findings clearly showed the first officer's aggressive control inputs generated aerodynamic loads exceeding the airframe's ultimate structural limits by a very significant margin. Over a mere 20 seconds, 5 rapid full left and full right rudder pedal inputs were made, creating extreme deflections. Each input exerted forces up to 200 pounds on the pedals, a massive amount of pressure for a pilot. These rapid reversals of direction at an airspeed approaching 200 knots created dynamic stresses far beyond any anticipated design parameters for the tail. The entire tail section effectively experienced G-forces well over its 2.5 G design envelope during the event. Engineers determined that the peak load factor on the vertical stabilizer reached at least 310% of its certified ultimate design load, a truly staggering figure. This meant the tail was suddenly subjected to forces over 3 times what it was initially built to safely endure before total catastrophic braking. The advanced composite materials, while strong for their weight, are inherently rigid and significantly less ductile than traditional aluminum alloys used in older aircraft. This rigidity meant the material could not flex or absorb the extreme energy from the rapid direction changes effectively. Instead, it simply fractured instantaneously. Stress concentration points around the attachment locations to the fuselage became critical failure initiation sites. Experts carefully analyzed hundreds of thousands of pieces of wreckage, specifically searching for distinct fracture patterns and any signs of material fatigue. Microscopic examination confirmed a clean, brittle break consistent with a sudden, overwhelming force rather than a gradual fatigue crack developing over time. The tail was designed to safely withstand a single full rudder input at maximum operating speed, but crucially, not multiple rapid alternating full deflections. This crucial design distinction was a major revelation for the aviation industry. The Airbus A300 aircraft manual itself offered no specific guidance on using the rudder for wake turbulence recovery, explicitly advocating for ailerons instead, a detail often overlooked by pilots in crisis. The forces applied during the sequence of 5 rudder movements were cumulative, each adding to the immense stress on the structure until its ultimate breaking point was instantly reached. This was unequivocally not a material defect in the carbon fiber itself, but a critical design limit issue combined with unprecedented operational stress. The ultimate design load for the vertical stabilizer was 31,000 pounds, which was catastrophically exceeded. The actual forces generated by the aggressive rudder inputs were calculated to be 75,000 pounds during the peak excursion of the rudder. This incredible 75,000-pound load was more than double the component's maximum design strength, proving its inevitable failure. The critical point of separation occurred at an estimated vertical load of 62,600 pounds, causing a complete and immediate loss of aircraft control. The aircraft was at an altitude of approximately 2,500 feet when the tail violently failed at 9:17 and 11 seconds. This deep understanding of the structural mechanics and the specific forces involved became absolutely central to preventing any future similar incidents globally. It fundamentally highlighted a critical gap in both aircraft design philosophy and pilot training concerning extreme flight maneuvers, especially involving composite material behavior under severe stress. The 265 lives lost ensured profound changes.